Inside any massive corporate logistics center, the chaos of thousands of moving parts is entirely an illusion. Every route, every box, and every shift is governed by a rigid, unseen mathematical architecture. Between 50 and 90% of all computations and business decisions made by corporate management rely on one specific analytical tool: linear programming. Despite the name, this has nothing to do with writing computer code. In this context, programming simply means planning. It is the mathematical planning of business activities. The exact purpose of this tool is to navigate a sea of feasible alternatives to guarantee an optimal result. It tells a manager exactly how to maximize a specific benefit or minimize a specific penalty. It exists because of a universal condition every business faces: scarcity. No operation has unlimited time, raw materials, or budget. Linear programming takes the messy reality of those limited resources and forces them to obey the unbreakable laws of mathematics. Before running any equations, an operations manager has to strip away the noise of the business environment. They do this by extracting three distinct components from their raw data. First, they define the decision variables. These represent the exact controllable physical quantities the business actually needs to determine, like the number of units to manufacture. Second is the objective function. This is the ultimate goal expressed as a single algebraic equation. Almost always, this function represents either maximum profit or minimum cost. Third are the constraints. These are the strict, quantified limits on the available resources. They act as the physical boundaries that prevent infinite production. To build this framework, we rely on the condition of certainty. We have to assume that our resource numbers and profit margins are entirely known and will not fluctuate while we run the numbers. Without establishing these variables, the objective and the constraints, management is forced to guess. At a global corporate scale, guessing always fails. To see how this algebra works in practice, let's look at a manufacturing facility. A toy company produces two different models, but both products must share the limited hours available in the factory's departments. This diagram organizes their raw data. Model 1 yields a $5 profit per unit and requires specific time in production, finishing, and packing. Model 2 brings in an $8 profit, but requires a totally different breakdown of hours. We establish our decision variables by assigning x1 to represent Model 1 and x2 for Model 2. Immediately, we apply a non-negativity constraint. Both x1 and x2 must be greater than or equal to 0, because producing a negative physical quantity of toys is impossible. Next, we attach our $5 and $8 profit margins to those variables. This constructs our objective function, maximize z, the total profit, which equals 5 times x1 plus 8 times x2. We now have a mathematical target. However, looking closely at this single equation, there is nothing stopping x1 and x2 from being a billion. To find the real answer, we have to map the physical limitations of the factory floor. We start with the primary bottleneck. The production department is capped at a strict maximum of 900 total working hours. Here, we apply the assumption of linearity and proportionality. If building 1 unit takes 1 hour, building 10 units will take exactly 10 hours. The math does not allow for economies of scale as production speeds up. We translate the production department's capacity into an algebraic inequality. 1 hour for every Model 1 plus 1.5 hours for every Model 2 must be less than or equal to 900. Notice how we simply add them together. This relies on the assumption of additivity. The total hours used is exactly the sum of hours used by both models, assuming 0 overlapping efficiencies. We repeat this exact translation process for the remaining departments. The finishing department has a 300-hour limit, and packing has a 100-hour limit. This creates a system of overlapping inequalities. By pinning physical labor hours to algebraic variables, we have successfully mapped the exact boundaries of reality for this business. To solve overlapping linear constraints, we move from algebra to geometry, a two-dimensional graph plotting Model 1 against Model 2. First, we plot the non-negativity constraint. Since we cannot produce negative toys, all possible answers are locked into the upper right quadrant. Next, we draw the production constraint. This line represents absolute maximum capacity. the company can only physically operate on or beneath this boundary. As we plot the finishing and packing constraints, each new line cuts away at the available space, restricting the company's options further and further. The resulting geometric shape, the heavily shaded intersection where all constraints overlap, is called the feasible region. Every single coordinate inside this bounded polygon represents a mathematically valid production schedule, but only one exact point inside it holds the maximum possible profit. Out of the infinite number of fractional possibilities floating inside that shape, we need to locate the single most profitable combination without relying on guesswork. This graph illustrates the feasible region shaded in blue. The final assumption of linear programming is optimality. The maximum profit, or minimum cost, will strictly always occur at corner point, or vertex, of this region. Think of the objective function as a straight line with a specific slope that slides steadily across the graph. Because the feasible region is bounded by straight, linear constraints, the furthest extreme of that sliding slope will inevitably catch on one of the outer corners. This drastically simplifies the math. Management doesn't need to blindly test every coordinate inside the shape. They only need to take the exact coordinates of those few outer vertices and plug them into their profit equation to reveal the absolute winner. The geometry of the feasible region removes human intuition entirely, mathematically proving that the perfect business decision always lies at the absolute edge of possibilities. This precise geometric and algebraic framework scales far beyond a factory floor. It dictates efficiency across nearly every sector of the modern economy. Marketing managers use it to allocate massive advertising budgets across different media formats, mapping constraints to maximize audience reach. Financial managers use it to select investment portfolios, treating risk as a quantified constraint while driving toward the objective of maximized returns. It is even used to solve complex blending problems, where chemical plants, petroleum refineries, and agricultural firms calculate the exact mixture of raw materials needed to hit strict quality constraints at the absolute lowest cost. Linear programming is an insight engine that translates the chaotic limitations of the physical world into pure executable geometric certainty.